number 4 symbolizes building a strong foundation.
I'm afraid we need to use math.
And now it's time for 4-4 in BC Calculus, the harder partial fractions.
Sorry, Halloween's coming up, and I've been practicing my laugh for my character I'm going to play at the door when I hand out the candy to the trick-or-treaters. So sorry about that Halloween laugh there. But anyway, now we're back in the studio, of course, and live from NSA, it's the evolution of Wade. Let's go ahead and transfer now to the real camera. All right, let's do some harder partial fractions. So in letter A, suppose this is a fraction, some kind of function that we have to integrate. All right, if you think back to 3-6 and 4-1, your first instincts are probably, hey, can't we complete the square? That does work back in 3-6 and 4-1. And let me show you board number 3 right over here. All right, you see that arctangent formula right there? It has to be a constant. You see there's a 1 on the top. It can't focus on my marker at the same time. But see how there's a constant on the top, 1 in this case, and then there's a constant squared plus a variable squared on the bottom. Okay, that's arctangent. So, yes, you can complete the square if there is a constant on the top, and you can make it an arctangent problem because it's addition. But if you notice the problem on the page, there's an x there today. Well, that thwarts arctangent, that's for sure. If I didn't mention that before explicitly, let me mention it now. There's got to be some kind of constant on the top. In the formula over there, it's 1 on top. If there were a 2 on top, we could have gotten away with it. Not a 2x, all right? So we're going to say not arctangent. Not when there's a variable on the top. So when you realize it's not an arctangent problem with no constant on the top for the numerator, the next thing you say is, all right, Mr. Wade's going to teach me like 3 different techniques in this chapter. Which one do I use if complete the square is out? Well, notice this is factorable. You always want to try that too. So this does happen to be factorable into, all right, 2 parentheses. It's our old favorite game called multiply add. X times x is x squared. 2 numbers that multiply to be 36 and add to be 12 are plus 6 and plus 6. Hey, this was actually a perfect square trinomial. It kind of completed its own square, if you will. All right, now we've got a better form there. And a matter of fact, let's go ahead and just write that as 2x over, you all know what x plus 6 times itself is, x plus 6 quantity squared. All right, so again, if there hadn't been an x on the top, that's actually pretty easy to integrate, even in the previous chapter. But as you can see here, it's not going to work. If you do use substitution, that won't work. So how do we set up the partial fraction decomposition? Well, because it's factorable in the first place, you know, oh, that's probably partial fractions. So that's the first tip there. This is the first time we've done partial fractions and actually gotten an exponent on our parentheses. We didn't have that last time, did we? Not in 4-3. That's the new twist today. How to handle that exponent on a base or a factor, all right? That is going to change things, actually. So I'm going to label this attempt number 1, and I want you to kind of appreciate the different things you could try here, and I want to show you why some of them are dead ends and one of them actually works, and kind of what to look for. All right, so partial fraction decomposition. How do I break this into a constant over something and a constant over something? So first of all, 2x over x plus 6 quantity squared. Okay, what was the system we used before in 4-3? Didn't we do one of the factors under a fraction bar plus the other factor under a fraction bar? I mean, that's how we've been doing it so far. Well, the 2 factors are x plus 6 and x plus 6. They are the same. And then didn't we put a capital A up top and then we put a capital B up top on that one? All right? And then if you can just find the numbers A and B, we should be able to integrate this. All right, so here's the thing. Remember the next step? Don't you multiply the entire problem by the greatest common factor, which will always be your original denominator, by the way. So don't we do x plus 6 quantity squared times the whole thing. So let's distribute to here, cross cancel, you get 2x. Distribute to here, one pair of x plus 6's cancels, but it leaves another x plus 6 up top where it's stronger than the bottom. So that would be equal a times the remaining x plus 6 that survives, plus b, and then we're going to get a cross cancellation here again, times x plus 6. A little funny that we have the same thing twice, and last time we had two different things. All right, so remember hide your a's, hide your b's. Okay, if I want to get a, I have to hide b, don't I? I want to hide b. What's the only number you could plug in for x that would give you 0b and temporarily hide the b? -6, right? At x equals -6, 2 times -6 is -12, equals a times, here's the problem, this parentheses is also x plus 6. So if you put -6 in for x, you get a times 0 plus b times 0. Does anybody see the folly? -12 equals 0. No, it doesn't. That can't be. Okay, so if I'm $12 in debt, I basically am breaking even. Yeah, that doesn't happen. Two different numbers can't equal each other in math. So there's a problem. We tried the technique we used last time. It didn't quite work. It needs a little bit of tweaking, all right? Last time, that's still good stuff. But for some reason, it's failing here. All right, let's try attempt number 2, because apparently that is not the way to do this problem. So, attempt number 2. All right, what do we have? 2x over x plus 6 quantity squared. And let's see if we can break that up in a different way. So another thought is to make it a over and just list x plus 6 only once, not twice. Because why would you list the same thing twice, right? That's redundant. So maybe we just list it once. Okay, now we could do the GCF and distribute it all the way through and try to solve this problem, all right? What happens? You end up with -12 equals 0 again. It gives you the same thing. No, it does not. That is impossible, right? All right, let's try attempt number 3 over here. So we'll say attempt 3. All right, let's try something else. 2x over x plus 6 quantity squared equals. So you can't break it up with x plus 6, x plus 6. You can't list just x plus 6 once, all right? Maybe we put a over and we just list the whole entire thing instead of breaking it down into pieces when there's a power on it. But then these two things would cancel each other, right? And you get 2x equals a. All right, well, So if I plug in 50 for x, then a is 100. But if I plug in 7 for x, then a is 14. If I plug in 0 for x, then a is 0. Okay, so you basically get a equals every number in the entire world. Okay, that can't be the answer. There should only be one answer, right? That's a dead end, all right? You don't know a, you don't know x. That's too many unknowns. You can't do it. What in the world is the way to do this problem? All right, now let's go to attempt number 4. Now that you've kind of seen a comparison from last time to this time, I want to show you a little trick. 2x over x plus 6 quantity squared. I want you to make two fractions and an addition sign. Okay, so it turns out that yes, the factors are x plus 6 and x plus 6, as we said. So what happens when you have a power is you list x plus 6 to the first, and then you list x plus 6 quantity squared. So you build your way up to the power. If that is cubed, you would do x plus 6 squared, and x plus 6 cubed. So it turns out you have to build your way up to the highest power one step at a time, and it works. All right? What genius thought this up? Well, he was the co-founder of calculus, the person who discovered calculus independently from Sir Isaac Newton. He is the number 19 ranked mathematician of all time. And he's also, his first name is Gottfried, and he was good buddies with the Bernoulli family. Number 19, Gottfried Leibniz. Leibniz was one of the two people, he and Johann Bernoulli, discovered partial fraction decomposition. And then also Leibniz came through and discovered this very special case right here, such a genius. X plus 6 on the bottom gets the A, and x plus 6 quantity squared gets the B. This actually works. So what's the common denominator, right? The common denominator is the original x plus 6 quantity squared. So we take the common denominator and we distribute it all the way through all three. This is the lowest thing in the world that would cross cancel with every single one of these. That's what the common denominator actually is. All right, so we distribute. When that group hits the first group, they would completely cross cancel, right? And you get 2x. That should always happen. When the x plus 6 squared hits the x plus 6, you will have a partial cross cancellation there, and you'll still have an x plus 6 next to the A on the top, because the top was stronger than the bottom. And then these two will multiply, they'll cross cancel, and you'll just get B. All right, now we're talking. So let's say when you have a quantity power that is higher than 1, that's when you build, okay? So let's say this is what Leibniz discovered. Quantity power, or exponent, greater than 1, build up, if you want to write that in your notes. You build all the way up to x plus 6 quantity squared, okay? And now we can use techniques from last time. So first, let's see if we can find A. Well, let's hide B. All right, there's a twist today. B doesn't have any x next to it. That could happen sometimes. If there's no x to B or next to B, we can't hide B. So let's go try to find B by hiding A. We can hide A because it has an x. So how do we hide A? Plug in -6 for x. So let's say at x equals -6, you would get -6 times 2 is -12, equals -6 plus 6 is A times 0, or you can just drop it, plus B. Aha, now that is a valid equation. Knocks out the A, turns out B is equal to -12. All right, now we got something. All right, now there's another technique I have to share with you today. Not just building up to higher powers, but a second technique, and that is sometimes you can't get your A's and your B's out of just this little substitution method. So what do? All right, once you've exhausted all options, which we have right here, we've done everything we could do. We got B, we didn't get A, that's all right. Take what you do know. You know B is -12. Take what you know and put it back into the equation and see if it's solvable, all right? 2x equals A times x plus 6, and instead of plus B, don't we know it's -12 now? So at least do that, and that will open doors for you, okay? Now, see if you can go find A. Well, we've always been taught in all of our integrated classes from middle school all the way up that if you have two unknowns like x and A, then you shouldn't be able to solve an equation that has two unknowns. Until today, under the right circumstances. Usually it's a no, but in partial fractions it's a yes. Here we go. All right, I'm going to distribute the A and write AX plus 6A minus 12. Okay, over here I've got 2x, technically plus what constant? Plus 0. All right, now I want you to notice this. If 2x has to be equivalent to AX, then A has got to be 2. Because don't you want a 2x on this side and a 2x on that side so they're equivalent? See, there are no more x's. So just don't worry about this right now. Don't worry about that. AX and 2x must match. Therefore, A equals 2. How clever is that? There's another way you could have done it. And by the way, you will get the same answer, unless you've done something wrong. The constant, wasn't the constant plus 0? What was the constant over here? Constants are things without x's, right? Wasn't the constant positive 6a minus 12? 6a minus 12 must be equivalent to 0 or this is not going to be equivalent. If 6a minus 12 is equal to 0, solve that. 6a minus 12 equals 0, add 12, divide by 6, you get the same answer. See, it doesn't matter which one you look at, you should get the same answer. Turns out a equals 2 in a very clever maneuver. Now, if that makes sense, awesome. If it doesn't, we're about to do it 2 more times, so don't worry, you'll get it. All right, so those are the 2 winners. Now, we won't go all the way through the problem the rest of the way, but what would you do? You would take your a and b and you would put them right back into here and here, and you would integrate these 2 instead of integrating that mass right there, right? And then it turns into, x to the first on the bottom, natural log, and not x to the first, well, it's x to the first but quantity squared. You'd have to bring it up to the negative second, do the whole integration that way, okay? We'll do some of that on the back page. So that's the new breakthrough, 2 techniques. How to use what you know to get something else, how to kind of line up those polynomials there, and then also how to build. All right, let's try our partial fraction skills. We've got x minus 1, x minus 2 quantity squared already factored for you. That's common as well. So you go right to your partial fractions. 4x squared over x minus 1 times x minus 2 quantity squared can be broken down into a series of 3 fractions that would help us make this integrable, because in its current state it is not integrable, but it's about to become integrable. One of my favorite calculus words. So this can be broken down into a series of partial fractions that don't even have a common denominator, but defying all logic can actually work and recreate the 4x squared if you went backwards. So first denominator, x minus 1. Second denominator, build your way up to x minus 2 squared. So x minus 2 to the first is the second denominator. And the final denominator is x minus 2 quantity squared. All right, now we put in the top. Now there is something I haven't mentioned yet. Didn't matter until pretty soon. It's going to matter in like the next problem. So I'll go ahead and give it to you now. All right, so in the top, we put a, but there's also something else there. The chain rule of the base x minus 1 is 1. You should have the chain rule, like put it in yourself. You should have the chain rule next to a to make things easier on the back end. This is an optional step, but I'm going to save you a whole bunch of steps at the end, okay? Let's look at this one as well. We always saw like capital B up here, but what you didn't realize was that it was capital B, and to set yourself up for success later on, the chain rule of x minus 2 base is also 1, all right? And then over here, capital C times what? Don't do the derivative of x minus 2 quantity squared by bringing the 2 to the front and doing the whole derivative. That's not necessary. Do the derivative or the chain rule of the base of the denominator, okay? Not the whole denominator. You see how the base of the denominator is just the x minus 2. Chain rule of the base of the denominator. We'll recap on that later, all right? And now remember, as you're doing this, you can pretty much set up any fractions you want. I can like if the chain rule happened to be a variable like x, I can put an x up here. You can make any fractions you want. There's no limitations. The only thing is, as we saw by attempt 1, 2, 3, and 4 in the beginning, a lot of them lead to dead ends and you're going to be tearing your hair out. I just wasted 10 minutes and I got negative 12 equals 0, something like that, right? Which is impossible, okay? Or I just got a equals b. Thanks, great. All right, so you can build these however you want to. I'm just giving you the best strategies that I've picked up over years of looking at this stuff, listening to how college professors teach it. My father taught it as a college professor, and the wisdom of Leibniz and all kinds of things, all right? So make sure you build to your highest power. Make sure you build in the chain rule of the base of the denominator, and that's going to really pay off with the fastest possible solution in the end. Take your common denominator, which is always found basically in the original integrand, and multiply the common denominator times this entire thing, which is, by the way, a skill that we did in integrated 3. in integrated 3 class, we had what are called rational expressions, like a bunch of fractions and you got x's on the bottom, and you play what's in your garage and you try to match all the garages, and then you basically just distribute the common denominator to the whole thing. We actually did this before. So that's going to go to everything. All right, so everybody gets an x minus 1 times x minus 2 quantity squared. So when this hits this, they all cross cancel. You get 4x squared. You always get the numerator of the integrand. When this group hits this parentheses, the x minus 1 will cross cancel, but you still retain the x minus 2 quantity squared next to the a. And you can drop the 1 in this step. Okay, that chain rule is going to pay off later, trust me. Plus, in the next one, when that group, that common denominator distributes to here, you're going to cancel an x minus 2 with one of those x minus 2's, but you still have 1 left. So you've got x minus 1, x minus 2 next to b, and I'll drop the 1. Cross cancellation. You never knew that cross cancellation would take you to such heights, right? This is why I've been preaching it all along. Can I say preaching in school? All right, teaching. So c goes there, and when this common denominator hits this fraction, the x minus 2 quantity squared cancels with that one, and you only have x minus 1 left. All right, and that is a better place to be for now. Now the only question is, can you find what constant a is equivalent to? What is b equal to? What is c equal to? All right, well, let's start off with a. We'll just start first in alphabetical order. Find a. Well, if I could just hide my b's, hide my c's, I could find a, right? Hey, what do b and c have in common? They both have an x minus 1. So if I let x equal 1, that would drop out the b and the c because of that 0 in there. Clever. So let's put 1 into there. 4 times 1 squared is 4. Equals a times 1 minus 2 is negative 1. Negative 1 squared is positive 1. Plus b times 0 plus c times 0. A is clearly 4. Check. We got it. All right, let's go try to find b. All right, so to get b, you need to hide your a's, hide your c's. So what do a and c have in common? Nothing. This hasn't happened yet. This is the first time this has actually happened to us. A has an x minus 2, c has an x minus 1. There is no number you could plug in for x that will simultaneously hide a, hide c, and reveal b. Is there? If you try 2, that'll hide a. That'll also hide b that we're trying to find. If you plug in 1, that'll hide c. That'll also hide b that we're trying to find. Aha, first time that's happened. Okay, not yet. That does happen sometimes. Let's go on to c. Let's find as much as we can in this phase. All right, could we find c? What do b and a have in common? X minus 2. So if you let x equal positive 2, you can hide a and b and find c. So take 2. Plug it in here first. 2 squared is 4 times 4 is 16. So when that side's 16, a times 0, gone. Plug in 2 for these two, but because of this one, b's gone. Plug in 2 here. 2 minus 1 is 1 times c. And you get c equals 16. Fantastic. All right. Well, we've got 2 of the 3. If we could just find the value of b. Now, wait a minute. What were we just talking about in that earlier setup when we discussed how to do all this stuff? Didn't we say if you don't find something, but you do find some things, you should take the some things that you know and put them back in and just see what we have so far, right? So take the 4 and the 16, put them back in, see what we got. Here, we'll go over here now. So 4x squared equals, we now know that a is 4. Put it in. 4 times x minus 2 quantity squared. Plus, we don't know b yet. Okay, b's unknown. B x minus 1, x minus 2. Plus, c is 16. Put it in. Try to use it. 16 times x minus 1. Okay, at least we've got this. So we're going to simply look for like terms and try to simplify this a little bit first. Now, if you're trying to like collect like terms, that kind of thing, you know, work this out, well, we need to deal with x minus 2 quantity squared. Now, if you're in a BC level class, don't you dare anybody distribute a squared across a subtraction or an addition. You can't do that. You're supposed to weed that out of your system in middle school. So do not do x squared plus 4. No. Isn't that a FOIL problem? X minus 2, x minus 2. Now, I do have some high expectations. If you're in a BC level class, you're very bright. Okay, you're here for a reason. So let me write this. 4x squared equals. Now, 4 times. I do expect people at the BC level to be able to, at this time in the year, FOIL this in their heads. It will save you a lot of time, trust me, all right? So I do kind of want all of you in your head to just know x times x is x squared. That minus 2x minus 2 more x is minus 4x. And then minus 2 times minus 2 is plus 4. So being able to look at like this quantity squared, think of it side by side and quickly do that in your head, that's going to be helpful to you. So let's try this one also. B times, all right, x squared, isn't that minus 2x minus 1x, so minus 3x, and then plus 2. And 16, we can go ahead and distribute that, 16x minus 16, okay? So we distribute the 16, we FOIL there, and then you'll also need to distribute the 4 all the way through and the b all the way through. So we're going to try to find out, like, what do we have so far, right? Well, we got A, we got C, we don't have B. This is the only way to do it. So notice I can only give you like one of these on a test because it's going to take you too long if I give you like 3 of these, right? So you won't have many of these, but they're very necessary. So distribute the 4, 4x squared minus 16x plus 16. Okay? Now, next part, here's one of my strategies. I'm going to show you a trick that I do when I teach this. Not all teachers do this, but my students like this. When you do b times x squared, I'm not going to write it here. I'm going to stack it under the 4x squared. It's going to make your life easier, okay? I'm going to put plus bx squared here. Okay, you'll like the strategy, trust me. That's going to be what, a minus 3bx, right? Negative 3bx. I'm going to put it here, negative 3bx. And then b times positive 2 would be plus 2b. You see what I'm doing? I'm lining up all my x squareds in one column, all my x's in another column, and all my constants without x's in the last column. And then finally, plus 16x, I'm going to put it in the x column. And then minus 16, all right? So we have this gigantic mess so far. We've got x squareds, we've got x's, we've got constants, we've got b's, we got x's. A lot of stuff going on here. Now wait a minute. This is all the stuff from this side. We've simplified pretty much as far as we can go. You can't do 4x squared plus bx squared because we don't know what b is, right? But on the other side, shouldn't all this mess over here total 4x squared? Now, you could put it here. My preference, I prefer to put it under, because this is kind of like, you know, back when you used to add numbers back in elementary school and you do the columns, you know, the hundreds, the tens, the ones, and you do plus. It's kind of that, actually. It's kind of that basic. Shouldn't all this total 4x squared? Let me put the 4x squared in this column. Isn't that 4x squared actually 4x squared plus 0x's plus 0? Okay? So 4x squared, I'm going to write it all the way out with the zeros and show you how these columns line up. X squared, x, constant. Now you can actually find b. We kind of hinted at this in the beginning of the lesson, but now you can really do it. You ready for this? 4 plus b should tell me how many total x squareds I have, right? Doesn't 4 plus b have to total 4? You see it? 4 plus b equals 4. I'm taking out the x squareds, but like 4 tacos plus how many tacos makes 4 tacos is what I'm saying, right? X squared equals taco. x squared equals taco. Never thought you'd see that in a math class, huh? So basically 4 plus b totals 4. Wait a minute, b is 0, which, by the way, we haven't had that happen yet, okay? Just because we couldn't find b over there does not mean it's always going to be 0. No, it could have been 72. But occasionally, you'll get one of your constants from partial fractions to be 0. It does happen sometimes. And it has nothing to do with the fact that we couldn't find it, by the way, all right? Sometimes you'll see 4 plus b equals 5x squared. Okay, 4 plus 1 equals 5x squared, so b would have been 1. Now, you don't have to do this column, but this is a good backup plan to make sure you did it correctly. I do all 3 columns because I want to make sure I did it right and didn't make a dumb mistake, all right? If you do this column, you should get the exact same answer for b, so you just pick any column, by the way. Negative 16, I'm going to take out the x's. Negative 16 minus 3b plus 16 x's should total 0 x's. Now take out the x's. Isn't that negative 16 minus 3b plus 16 equals 0? Isn't that what we're finding in this total column here? All right, the 16's cancel. Negative 3b equals 0. Oh yeah, b does equal 0. Now if you get different values for b in different columns, something went terribly wrong because you should get the same thing. You also could have picked this column here. 16 plus 2b minus 16 should total 0. Again, the 16's cancel out. That's rare that they cancel out in 2 places. That's interesting. 2b equals 0. Well, what do you know? It doesn't matter what column you pick. You end up with the correct answer for b. So, worst case scenario. You work out the FOIL, you distribute, you make your proper columns, and then you put this one to fit the columns, and that's how you find b. All right? Yes, there are partial fractions that are even worse than this one. I worked out some of those and I thought, no, I don't need to give that to a BC class in high school, okay? Because they were so messy and so difficult. I mean, you wouldn't get them unless you're going to Yale, Harvard, Princeton and taking Calc 2. They might give you some that bad, all right? But I didn't even see some that bad when I tutored Vanderbilt students in Calc 2, so don't worry about it, all right? This is the hardest it's gonna get, and anything harder would never be on the AP test, okay?